The purpose of these matchmaking meetings are to really listen to teams present, get a sense of who your other, the cohort of competitors are, what kind of skills they might need. And the next team we have is iTrap CO2. I love the name, and that's Lisette Cordova.
Perfect. Let's review it. First, thanks for the opportunity. I am Diego Guevara on behalf of Bernardo del Campo, representing iTrap CO2, a team from Advanced Renewable Technology International ARTi from Prairie City, Iowa. I would like to share a robust group of smart individuals and experience in the biochar world. We have more than 50 years of combined experience and studies in biochar, and we are convinced that biochar is the best tool we have to fight climate change. Now, how we make biochar? We heat biomass organic material up to high temperatures in the absence of oxygen in a process called pyrolysis. With pyrolysis, we obtain three main products: syngases, oil, and biochar. We pyrolyze the initial biomass feedstock, and we transform up to 50% of it to a stable solid carbon, bearing that 50% of CO2 into soil. To make it possible, we have developed our technology and systems. Our innovative solution has several strengths, and just to mention some of them, is that it is a containerized mobile unit, so it can be virtually placed anywhere around the world. It is able to process any kind of feedstock, and we have pyrolyzed a broad range of biomass in the past successfully. And it is mostly an automated operation with minimum labor. And with this, we sequestered up to 4 tons of CO2 equivalent per day, and with our simplest unit. Finally, I would like to express our ability to implement our technology and reactors worldwide. Here's a map summarizing our presence internationally. We certainly seek to continue expanding our affordable technology for climate change and benefit the communities around the world in the near future. I want to close this quick presentation with some pictures of our solution to climate change worldwide and our reactors implemented in different sections and parts of the world. Firstly, you will see Hawaii, another reactor in Canada, Ireland, and China, just to mention some. Here is our contact information just below, and we are excited to know which location will be next for us. Thank you.
Excellent. Thank you, Bernardo, and iTrap CO2. So again, just as a reminder, if you see a team that you're like, oh, they're looking for, a skill set that I have, note their team name down. So when we end the presentations, you can go ahead and talk to them in their breakout room. Okay, so the next team we have is Team Atmoo. And that is it's beatrixcastelar.
Yes, yeah, thank you. Well, thanks for the opportunity to present to Atmoo. So our technology for capturing CO2 is based on macroalgae farms in the sea. Algae absorb CO2 dissolved in water by photosynthesis and use it to grow and to synthesize complex carbohydrates. At least 20% of dry algal mass are composed by carbon captured by dissolved CO2. So for the next step, the processing, we extract protein and pigments from these algal mass that could feed people and animals, reduce methane, and of course an important greenhouse gas. But especially we are focused in the byproduct of this extraction that are rich in polysaccharides, and those polysaccharides are converted in monosaccharides in this step needed to the next step, sequestration step. Finally, the sequestration step is guided by a special bacteria bacteria fed with those processed carbon, and these bacteria retain the carbon and transform it in a biodegradable plastic that could replace all the million tons that tons of petroleum-based plastic consumed by us daily, reducing, of course, available and emitted CO2, as you know, other than plastic pollution in the oceans. In summary, we expect that 30 hectares of algae production can capture 1,000 tons of CO2 per year and retain it in 150 tons of bioplastic per year. One of the key aspects of Atmoo is that fresh water and arable or forest lands are not necessary, and instead we have a lot of areas, oceanic areas for that. So we are looking for people with expertise in industrial process and CO2 balance to help us to reduce even more our own CO2 emission through the entire production chain. So that's our contact, and thank you.
Thank you, Beatrice. William, are you able to share from Envirohome? Are you ready to present now?
Oh, okay. Team Envirohome. Team Envirohome, I'm williamfears from Dallas, and our idea is going to employ the use of ocean alkalization for purposes of changing the pH of portions of the coral reef, with intent of slowly returning reef calcification to more pre-industrial levels using medium-level pathways. And this was seen in Nature, volume 531, by an article on a proof of concept. The alkalization process will closely be monitored by experts in coral reef health, while at the same time achieving proof of concept and safety and benefit to coral ecosystems. The team is based on the concept that traditional engineering solutions wouldn't be able to scale up enough to sequester the amount of CO2 necessary for the timescales required to slow global warming. Our method will be based on Dr. Rebecca Albright in Nature and 2019 proceedings of ocean alkalinity and alkalinity enhancement written by Antonio Gagarin and other contributing scientists, which I would highly recommend. We know that acidification of oil reefs is projected to cause net dissolution of calcium from a state of net accretion by the end of the century. And Dr. Albright was able to show that the restoration of pH closer to pre-industrial conditions resulted in net community calcification using controlled release of sodium hydroxide over a small area of the Great Barrier Reef. My team, using guidelines from these papers and others, intends to demonstrate that medium scale targeting of ocean reefs will cumulatively sequester large amounts of CO2 into argonite. This approach will advance public education, assess market incentives and pathways for ocean alkalinization, and at the same time help develop policy measures that will enable it at scale. We would attempt to release the optimal amount of sodium hydroxide, initially from small ships, 30 to 36 foot ships at various distances from the reef edge. And then you use a passive tracer with a benign dye and be employed to assess the effect of alkalinity uptake with different concentrations of base at different distances at high and low tide, and let the tide do the work for you to measure the width and the length of the reef affected using dye dilution techniques and argonite production. It's only fair to say that I'm 75 years old. I have a rather significant heart disease. It's also fair to say that any team attempting needs money. Ultimately, I need $50 per net ton removed. Really, 5 million would probably cover it. My goal is primarily to make certain that this approach gets the attention that it deserves. I want to join a team that's doing this if they already are, or I'm willing to take on a team leader who can make it happen. If by some miracle we win, the money will be used to carry forward the work. Public outreach and engagement can ensure social licensing and public funding. This method has a probable advantage of improving coral health, while at the same time reversing ocean acidification because of the strength of the base, and improve fisheries and stop the damage caused by CO2 on the ocean and land. I don't think we have time to debate 50 years. We need to get started with what we know now and monitor closely for what we don't know. Thank you.
Thank you, William and Envirohome. Again, reminder, if a team resonates with you, note their name because you're going to get a chance to talk to them after we're done with the pitches. Okay, the next team we have up is Aquarius. Team Aquarius and Anthony Tatum is going to be presenting.
Okay, so the team name is Aquarius. We actually are not an ocean solution, but we would fall under land, I think, or direct air capture. So we're sequestering CO2 by converting agricultural, forestry, and municipal waste to biochar. Right now, there are 6 collaborators, and you'll see at the end that we're looking for more. So summary, how do we collect the CO2? We let the earth do it for us. I think that's the beauty of the solution. The agriculture, forestry, and municipal infrastructure already exists and already is capturing, gigatons of CO2 actually. But typically it just erodes and then goes back up into the atmosphere. So the way we process it is we take the waste from those 3 systems and process it in a pyrolysis reactor. So you've already heard this, which is pretty cool that other teams are doing it also. But that produces biochar, and biochar is a stable form of carbon that can be used for marketable purposes like soil amendment, filtration, or batteries, or it can be buried for carbon credits. So one of the main things about our organization and actually newly founded company is the reactors. You call it a reactor, but it's actually like a kiln or a furnace. But it's fun to call it a reactor. I never thought I would be building reactors one day, but our current reactor processes 60 tons of biomass per day. That's pretty large. It can produce 1 megawatt of power as a byproduct of that, along with all of the biochar. We are currently building a smaller, less expensive reactor that can be just used by a single farm or a small forestry service. We're intending for widespread use of that. And then we're also reaching out to developing countries with the most accessible design, which is really just a few oil drums, and you kind of start a fire and create biochar that way. We hope that ends up providing free energy to drought-stricken and deforested locations. We're looking for engineering or AutoCAD design to help with making the design of the medium-sized reactor official so we can get it into production or at least prototype built ASAP. 3D printing, because we foresee in the future if we're going to need about 50,000 reactors to get 1 gigaton of CO2 out of the atmosphere per year. And the manufacturing of that is going to be difficult. So if you know anything about 3D printing or how to make that a faster, bigger process, that would be great. And then crypto, Bitcoin and Dogecoin. So we're not just trying to build 50,000 reactors. We're not just going to be a reactor company. Essentially, we want to build 50,000 small businesses. So when you buy a reactor, it's going to be profitable for you. And one of those ways is using the extra energy to mine Bitcoin or Dogecoin. Here's my contact information, and I look forward to hearing from you. Thank you.
Great, thank you, Aquarius and Anthony. Okay, the next team that we have up is HONU Engineering. Jonah Heller will be presenting.
Yep, I'm right here. Thank you.
Okay, hey, Jonah.
No slides. My name is Jonah. The company is HONU Engineering. We are a CAD drafting and construction management provider based in Hawaii. The company was founded in 2016, named for the Hawaiian sea turtle, HONU Engineering. We have specific experience with projects ranging from biodiesel stations to pool equipment rooms to utility scale solar facilities. The HONU Carbon Removal system will draw seawater from the ocean, extract the carbon, repurpose it for long-term storage, and provide the excess carbon to other secondary users. We have proof of concept, and we're looking for human capital as well as financial capital to build the prototype. We're looking for 3 engineers, mechanical, electrical, and chemical, and 1 veteran rock star engineer entrepreneur to provide guidance, because it's not enough to just build it. I know this is a global audience, so we can get started remotely via Zoom, but eventually you'll have to come to Hawaii, at least for a visit. We have local resources available at the University of Hawaii Maui College, where I'm also the CAD teacher. We believe climate change is a tremendous threat to humanity, and we're here to put our hand in the pile and make a contribution, fighting climate change on both fronts, expediting global transition to clean energy, and removing carbon from the atmosphere ocean. Thank you, ROPA, and the good people at XPRIZE for creating this opportunity. And thank you everyone on this Zoom call today for making your contribution. We're all in this together. Once again, my name is Jonah, and the company is HONU Engineering. Thank you.
Next team up is Team Repair or Repair. I see what you did with the name. Amir Shiner is the presenter.
Hello.
Hi.
Yeah, it's Repair.
Repair.
Hello, my name is Amir Shiner, and I'm the CEO of Repair, a young company in the field of direct air capture. And thank you very much for the opportunity to present here today. I'm talking from Israel. Direct air capture is a notion that is now in consensus. There's no question that it has to be part of an array of solutions in order to effectively fight climate change. I don't need to elaborate much about that, but this is something that we are very much involved in. The main challenge in direct air capture is how to make it economically viable, to scale it up in a way that will be affordable. The number the whole industry is looking at is below the $100 per ton CO2. And the issue, of course, is scalability, how to make it scalable at a reasonable, affordable price. This is where we come to play. We develop a scalable solution for direct air capture that is based on electrochemical technology that is coming out of the laboratory of Professor Yushen Yan at the University of Delaware in the US. The cell design is inspired by alkaline exchange membrane, fuel cells, and battery design, something a hybrid inspired design, clever in its simplicity. And the way it works is the following. In general, in principle, air is streamed into the cell, the cathode side, where CO2 binds to the hydroxide that's produced by the cathode to form bicarbonate and carbonate ions. Then CO2 depleted air is pushed away from the cathode side to the atmosphere. The bicarbonate ions are transferred through an anion exchange membrane to the anode side, where a reverse process takes place and pure CO2 is streamed out of the exhaust of the cell. The process is relatively straightforward in small scale and doable, very much doable in a larger and larger scale. It's a continuous separation, unlike some other direct air capture approaches that are more batch-like approaches. We are completely electrically driven. No additional heat energy is needed for regeneration. We operate around ambient temperature, which is also unique. It allows us to use lower cost materials for the electrodes, for the membrane, and so on. And of course, it is highly modular and scalable to gigaton scale. We are at proof of concept stage. We showed at a lab scale preliminary proof of concept that the technology works. Not only it works, but also it is very promising in terms of the energy consumption, and with a promising chances of reaching well below the $100 per ton CO2 that I mentioned below, which makes the whole project very, very interesting. We are 4 members in the founding team, Professor Yushan Yan, and the 3 entrepreneurs. All of us are scientists, engineers, entrepreneurs, and managers with many years of experience, focused on electrochemistry and the electrochemical cell. And what we need is to complement those capabilities and that experience with experts and teams from the sequestration, either by burial or by using the carbon for products. So please, if this is something relevant, please contact me, and this is my contact details here on the screen. Thank you very much, Rupa, for having me.
Thank you for presenting, Amir. Team Shadokx is up next, and that's Alexander Picourt. Sorry if I pronounced.
No, it's okay. It's okay. Hi, Rupa. Hi, everyone. Thank you, Rupa, for all the things you do, and thank you to all the competitors. I'm really impressed by the level and the solutions that are already presented. So I'm going to share my screen. Okay, just tell me if you see it.
Yes.
Okay, so Team Shadokx, we're about 15 persons, mainly mechanical engineers from France, from Germany, Switzerland, and also in the US. So our project is to remove carbon from the atmosphere and take it to space, and then convert it into fuel. So what we want is to do CO2 removal to fuel space conquest. Why are we talking about space? Well, in fact, we know that for million years, carbon has been stored underground, in the underground of Earth. And then those 3 last centuries, we took it out from underground, ground, air. And what we want is to go to the next stage, which is space. We don't want to spend energy to bring back CO2 underground or under another thing on Earth. So that's what I call a unique and historical configuration, and also what we see right now, a unique and historical convergence. 2 things, 2 forces that are converging. One's the emergency of the climate change, and 2, the global movement in favor of space conquest, where new solutions are required. So how do we want to treat CO2 from space? Well, we want to create a kind of gas space station. Here you have a short drawing where we can see a system made by a planet and 1 atmosphere. And then we have this gas space station, which is made of a big space needle and a structure you can see here where we will treat CO2 and put it into autonomous space tanks. This process is reversible. That means that we can, from those autonomous space tanks, so we can send gases or other things on a planet. So schematically, here we have the planet, here we have the atmosphere, here we have the space needle where we have this air transfer through the space needle. Then here we have in those little sticks, we can see here a catalytic conversion of CO2 to transform it into chemicals and fuels. Those chemicals and fuels are stored here in tanks at the extremity of the catalytic converter. And then those tanks, we can send them where needed. Okay. So how is CO2 sequestered? Well, in fact, it is not sequestered because it is simply taken out of the system Earth. Okay. So we are looking for different expertise. What we have made already are mainly hypotheses on the mechanical construction of this structure, and we need expertise to validate and criticize those hypotheses. We have made choices in design, and so we need to have a critical point of view. So we need expertise in thermal and mechanical space engineering, atmosphere sciences, also chemistry and CO2 conversion process. That's what I said now here. If you are a XPCR team and who has developed a solution and you think that you can bring that into space, so we can convert CO2 directly there. So we can have a talk about that, and also expertise in biology, because of course, if you take out something from a system, then you have to regenerate maybe what you have taken out, and so we have to find a good balance. So here you have my address to get in touch with me. That's it.
Next up, we have Team Groundproof, and Derek Parent is going to present.
We are from SCAR, Sonic Carbon Absorption Rapidly. So we observed some things. We observed that carbon dioxide is relatively denser than most of other gases in the air, and it can be displaced from the air at a particular frequency of sound waves, that is somewhere between 80 hertz to 60 hertz. And obviously it is easier to capture carbon dioxide once it is displaced from the air and separated from it. So what process do we use? We have this cylindrical chamber in which we are booming sound waves at a certain frequency, and then these pressure waves concentrate CO2 at local regions, and after that we kind of spray or fill the chamber with zeolite aerosol, which then absorbs carbon, and then it can be further treated or processed. So we are at proof of concept stage, and we have our research papers on carbon fluidization and how to capture it using sound. And also we are using zeolite as a mode of absorption because amine solutions are more complex and difficult to treat. So for the sequestration part, we have not figured that. We're still working on it, and we're flexible with the sequestration process, though we have been exploring a field in which we can actually combine Sabatier reaction with flash graphene process to make graphene from methane. And wait a second. So obviously advantages of the process does not utilize expensive tech, increase rate of capture, increased amount of capture, not energy intensive, and all over low setup cost and low cost of capturing carbon, and obviously increase capturing cycles. So we are Team SCAR from India. I'm Yash, I'm a student entrepreneur. We consist of 2 mechanical engineering students here from India and 1 CS student from MIT, and we are looking for a chemical engineer. So that's pretty much it. Thank you.
Thank you, Yash. Okay. And gonna remind you again, if you see a team that's, seems like a good fit and that you'd like to speak with, just remember to note their name down for the breakouts. We can move to the next. So we have Mad Matt's Motor.
Hello. Can you hear me?
Yes, we can.
Great. All righty. So on my display today, as my picture, I have my setup. These are 2 Mott transformers connected up to some capacitors, connected to a waveguide, making microwave plasma. So my method of capture is CO2 dry reforming through microwave plasma. And then how CO2 is going to be processed. So I'm going to go in the more of the automotive sector, well, direct air capture. But so the CO2 is processed through the combustion engine's exhaust and atmospheric air, turbocharged into microwave plasma. And then the plasma is pumped into a reactor, and then it is captured, and then it will be sequestered deep into aquifers. So that's what I got. And I might have a small display of my reactor. Everything is basically made out of recycled parts for right now. Some numbers, a regular automotive vehicle will put out 4.3 tons of CO2 emissions a year. So you get one of these going through a lot of cars, you're going to capture a lot of carbon. And kind of works on the process of diff. So that is a diesel exhaust fluid. So it's kind of like along those principles, but a little bit more high voltage. But yeah, so here's my small reactor that I'm going to get going. This is just a recycled propane bottle. So I'm going to pump the microwave plasma into this propane bottle and see what I get on the other end. I have obviously developed the microwave plasma, and I have turbochargers, and I'm just going to have to get it all connected together. So that's what I got. So Mad Matt's Motors is looking for a tech in physics, engineering tech in electrical and mechanical engineering, CAD design, and just maybe a regular helper technician that wants to do the odds and ends. But yeah, I'm the sole proprietor of my team, and I loved everybody else's pitches so far. Thank you. And you can get a hold of me of Mad Matt's Motors at Gmail. All you have to do is type in MADMATTSMOTORS to Google, and you can find me. Thank you.
Okay, thanks, Matt. In the meantime, if we have one more team, that is Team Undesert, and Nicholas will be presenting.
Me, thank you, Rupa. I will start sharing my screen now. Hi, everyone. My name is Nicholas Seed. I'm the CEO of Undesert.com, and we have a project that we hope will change the world's deserts into forests. And how do we do that? It's because we have a technology that can convert dirty water, which is, we say dirty water, but it really can be any water, seawater, subterranean salty water, production water, you name it, into water that's suitable actually for drinking, but we can use it to water these trees. Okay, so I'll just quickly run through the presentation. We know the problem, don't need to cover that. So this is our technology. We call it SWAP. It's a solar desalination technology that takes the sun's energy and converts it to, uses that sun's energy to evaporate the water and recondense it into clean water. And what we have done is demonstrated this in Sharjah in the United Arab Emirates. And you can see a picture down here where it's a really, really bad desert. And we've converted it into a small farm. And that's something that, in Sharjah, in the United Arab Emirates, this is like, whatever, growing a farm in the desert. It's like a miracle for them. So they're very, very happy. They've actually want us to 10x the size of our demo here. What we've calculated that we can do is to use this wastewater to convert production into a farm in the US for trees at a price of $5 per ton. And so this is something that we think we could, not only is the lumber valuable at about $100 a ton, but we could do this with 1,000 trees per acre, and that would allow us to capture enough carbon where's my slide on the scale of, my computer's frozen. Okay, it's moving now. Okay, anyway, moving on. I've got more numbers further on. We're going to be targeting obviously the Southwest, which has really good sun, but then of course there's deserts all over the world. You know, Saudi Arabia, the Australian outback, the Mojave in the US and so forth are all ripe for converting those into forest land. There's really nobody doing this direct growth of trees in the desert. So we think that it's something that we have a unique opportunity for. This is a flow diagram of our water process that we have 2 patents on, and it's something that is working. It's working right now. So we got a couple of nice endorsements from all of these big government organizations, and our team is here. This is me. This is my scientist co-founder Hill, and we're ready. It's like we are right now planting in the desert in Alamogordo. We will be expanding that to El Rito. This is what we need to demonstrate to win the XPRIZE. We need 3,500 trees, and that will fit in 5 acres. There are, if you imagine, how does this scale? If we were to take this and then rubber stamp it over 1 square mile, we would be capturing 82,000 tons of CO2 per year. It would take quite a few trees, but that's really no problem, because this process that we're going to be demonstrating will demonstrate the cultivation of seeds and saplings from these trees. We already have a partner in New Mexico that is selling Christmas trees, basically, tree farm. So they know how to grow trees in the desert and harvest those seeds to grow more trees and saplings. That's it. So what are we looking for? We're looking for people with land, with people with desert, people who are involved in forestry, who know how to manage soil, who know how to sequester carbon using the leftovers. And I obviously am going to be contacting that team we heard from earlier. These trees are going to be dropping lots of leaves and branches and so forth. And how do we keep it clean? Biochar is one possible solution to that. It makes a lot of sense. And that's us, Undesert. Hopefully you can check out our website, and my email's right here. So thank you very much.
Okay, thank you, Team Undesert. Laura from Team Mortar, I think we can have you present the next matchmaking session, if that's all right. We have one more team left today, and then we'll get into breakouts. So that's Team MDAC. Kevin Thomas, are you ready to present?
First off, thank you very much. Appreciate it. It was a last minute addition, so I appreciate the flexibility. I greatly appreciate it. A lot of really good ideas. I think all of us know that there's not a one solution that's going to solve this problem. And I think each of these solutions certainly play a role in slowing down and possibly reversing climate change as it relates to CO2. My name is Kevin Thomas, Team MDAC, creatively named after micro direct air capture. We've developed a micro direct air capture system. We have a provisional patent on it currently. I've been working on it for roughly 3 years. It's gone through 2 separate iterations. This is the second of the 2. So CO2 capture method, as is described in the name, it's direct air capture. The micro direct air capture system employs an appliance the size of your typical air conditioning unit. We designed it this way specifically so that it could get closer to the concentrations of carbon in population centers. And so, a lot of the larger scale solutions are positioned in areas where CO2 has already been diluted within the atmosphere. And our approach tries to get closer to the emissions levels to capture it directly out of the atmosphere before it has a chance to get diluted. So we're small in size, again, allows for broad scale, reduces the cost of development and entry into the market. Each unit is interconnected, so it leverages a swarm intelligence technology to tackle CO2 concentrations at the source. So if you think of it this way, you look here in Fort Lauderdale at the top of an apartment complex. There's plenty of real estate to put these units on. If a delivery truck that pumps a lot of CO2 emissions and unwanted gases into the air parks on one side of the building, the units on that side of the building will communicate with one another to tack the CO2 emissions, while the units on the other side are conserving energy for higher concentrations to create that right energy consumption balance. So you receive a net negative solution. It's energy efficient, utilizes an electric DC power collection and storage framework, has a battery pack on the bottom. It is surrounded by photovoltaic cells, which collect and store the energy. And then it has, each of its components are interchangeable and operate independently of one another. So 6 fans don't need to operate at the same time. If the CO2 levels are not high enough to demand that sort of energy consumption, one can run or all 6 can run, depending on the measurements of CO2 in the surrounding atmosphere. Versatility is critical in this design. Technology in this space is adapting quickly. So this has been a modular design. There are 3 primary solutions for sequestration. Solvent absorption, which is used for larger factory type solutions. Solid sorbents, which is widely proposed for direct air capture, and then some really innovative things coming in the membrane space, which is under development and promising. And our interchangeable CO2 filter allows for the adaptation and advancements in this space. So that filter is interchangeable. It can be pulled out, can be replaced, it can be redesigned and fit into the path airway for collection of CO2. Finally, CO2 collection method, storage and processing. The CO2 is captured by the system, be compressed for transport and stored via tanks. There needs to be a multi-phase implementation for this. First, it will be localized tanks that capture this. We'll leverage industry expertise. We're not proposing we'd be responsible for disposal. There are a lot of companies out there that are good at this. We will partner and leverage their existing expertise for that. But ultimately, we view this as utility, much like trash collection or natural gas, where infrastructure can be developed to pipe the unwanted CO2 into reservoirs or systems for broad scale collection and managed accordingly. And so then finally, what is it that we need? The micro direct air capture system is a design concept that's working towards prototype development. We need bright minds to help us get there. So skill sets that we need to take us to that next level are engineering in nature, mechanical, chemical, software, legal, obviously intellectual property protection, business and environmental concerns, and finally, regulatory and compliance. We view this as a partnership with the various governments because to tackle this problem is going to take a true infrastructure mindset, and we believe that we can play a small role in that. Contact information is at the bottom, and thank you very much.
Okay, great. Thanks, Kevin. All right, everyone. Thank you for everyone who presented today. We'll be holding another one of these in a few weeks. And, hopefully you've found them helpful. We also welcome feedback on what you'd like to see for these sessions.